Hello everyone, welcome to today's ASRG webinar. My name is Nikolaos Kakouros from ASRG Stockholm. Before we jump to today's presentation, I'd like to tell you a little bit about ASRG. ASRG is a non-profit organization founded a bit more than 4 years ago to support the development of the automotive security industry. We have developed a platform and a community for the automotive security industry, the academics and organizations, to share knowledge, communicate, and build value with collaboration. This is a community for you, built by you, with a goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Moving on to our today's guest, it is my pleasure to welcome Joar Jacobsson. Joar is the head of the Cyber Domain and Process Development Department at foreseeti. Joar is responsible for designing, modeling languages, and developing the methodology of threat modeling and attack simulation used in securiCAD. In case you have questions during the presentation, please write it into the chat window. After the session, we will have some more minutes for questions and answers. Joar, the stage is yours.
Okay, thanks for the introduction and welcome everybody. As mentioned, I work at foreseeti and we are working with or developing the securiCAD tool, which is a CAD tool for threat modeling and attack simulation. And therefore, in this session, I would like to take the opportunity to present our view on the threat modeling concept and a bit about attack simulations. And then in an upcoming session, I will show a bit more about the vehicle industry and how you can benefit from this. But to begin with, let's look at the threat modeling concept. And to do that, I usually use this guide to cyber threat modeling. This one comes from CSA Singapore. It's a pretty good description, and I don't have any other connections to CSA other than that. But in this one, actually, we have a description of a threat modeling methodology and different aspects of that. But the important thing I want to highlight here is this high-level architecture map that we see here. So this is a map that is kind of similar to what the material that we get when we are using the design approach to threat modeling. And that means that we don't have any pre-collected data of live running systems. That's also an option, of course. But when it comes to the design phase of different solutions, this is the kind of data that we got. And of course, this might seem a bit far from industry-specific applications, because we have web application, we have firewall router, we have a database server, and SQL database, and so on. But if we look at this in a more general way, it is really not telling us anything really about what about the implementation of these different bubbles here. It is only saying that we have some front-end application where external users are able to connect to. Okay, this one says HTTP, but the important aspect here is that this part of the solution or the architecture is intended to be reachable. So this is the user interface really. And this one is called Internet here. And then we have a DMZ where the web application makes some connections over a firewall and a router to some internal web server, possibly, but the map doesn't say. And then there is communication into another part of the architecture called the corporate network. But if we think about an industrial control system, then this would be the lower part of the solution where the production is actually managed. So from a SCADA point of view, I would say that the SCADA solution itself would reside in this corporate network tier. And then we have the SCADA DMZ with intermediate systems that the office staff is intended to interface with. And then we have the office or the engineering zones in this outer tier here. So thinking about threat modeling then, the intention is to really set up a model that is representing this structure in a proper way. And then we also would like to take a look at both the structure, but also about the different properties of these modeling objects here. So if we flip over to securiCAD Enterprise here, we see that we have a set of models and so on, but I would like to open this one. And this is the model that is representing the map that we just saw from this conceptual map from this Singapore company or authority. And we see that we have something here, which is representing a server. And we have something called a connection rule here. This connection rule is really defining what communication is possible in and out of this area of the architecture. And before we go into what different objects, or I will actually not be all that detailed about the different objects because or the purpose of them, but what I would like to show is that we have an application object here. And if we look at the preferences, we see that we have something called attack steps. And attack steps and defenses are things that the attacker would like to achieve. In this case, for an application, we have things like authenticate and modify and local connect and so on. And the opposite, so to say, of attack steps, that's the defenses. So when an attacker is starting from a certain starting point in the architecture and reach this object, the attacker is expected to attempt these different attack steps and possibly might achieve them depending on earlier achievements. And the defenses are the things that makes some of these attack steps or all of them more difficult, or in this case with the disabled defense here for this application, it makes it impossible. So if I think about the more industry-specific view of an application, then these attack steps here, they are not really, it says database API in this case, but it's nothing here that really is tied to this being a database API. It is merely an application in a certain position in the model that might be reachable by the attacker. And if the attacker can reach this, you could possibly authenticate, you could possibly gain full access, that's the final goal of it. You could possibly modify it, or you could connect to it over the network and then attempt to do additional attack steps. So except from the location in the model of this application, when the attacker can reach here, the attacker need to make use of a couple of these attack steps or operations in order to proceed to other applications or gain access to other identities and so on. And if we close this one and we take a look at an identity, for instance, we have what I want to show here is that we have a different set of defenses. So for any kind of identity, which is, well, you could call it a user account. For any type of identity or login, you can assume it, but before you do that, you need to attempt to assume it. And if multi-factor authentication is enabled, you need to succeed with bypassing that in some way. Yes, and then we also see that applications can be hosted by other applications. So here we have this operating system, and we have on the operating system we have child applications. So we have database API, we have possibly network clients, we have a database client, and so on. And if we think about, let's say, a monolithic piece of device, then it could be the case that the operating system is so tightly coupled with the applications it's presenting to the outer world, so that this application could be seen as one application that is accessible from the nearest zone, so to say. Then we see that we have other pieces of modeling objects here, and we have this data object, and data can be read, deleted, and denied in different ways. And if we look at this guide again, it's of course corresponding to this SQL database here. It doesn't have to be SQL, but there is an application that, if you compromise that, allows for access to this SQL database, or this database content, really. Then, in order to do this, we also would like to add vulnerabilities. And is there something I would like to say before I go there? No, not really. So we have applications that are interconnected with other applications, and we have these arrows represented by allowed communication between applications and between networks, and sometimes bridging network zones or tiers. And if we then think about the presence of vulnerabilities, we see that we, for instance, in this case, we see that we have something called an unknown server-side vulnerability. So this unknown server-side vulnerability, it also has got attack steps and defenses. So there's properties to this one, which is connected to this database, in this case, API application. And if we look at the defenses or the properties here, we see things that an attacker would like to make use of this vulnerability. And the defenses are mapped to different properties, telling how useful is this vulnerability really. And if I again think about the industry-specific area, then sometimes when you think about vulnerabilities, you think about official CVEs or CWEs, and things that are well-known and published vulnerabilities or security issues with well-known and widespread, more or less traditional applications. But since it is possible to, or even recommended to, adjust these defenses to that way you can represent even an imagined vulnerability, or if there is a security issue with a certain implementation and you know about it, then you could say that you could adjust the properties here to say that if an attacker can reach this position, it is expected that this vulnerability or security issue would allow the attacker to do a certain thing. but it is not possible technically to do other things. That means that you could adjust this vulnerability according to what you know about a particular security issue. So that means that you could say that, okay, local access is required. That means that you cannot make use of this unless you already have a foothold in this application. Is it expected to have an availability impact or only a confidentiality impact? And so on. And also we have another defense that is called remove here. So remove is of course the main recommendation for remedy of a security issue. But if we think about the threat modeling approach, it is possible to put a probability to any of these defenses. And that means that if we are looking at a high-level architecture diagram, and we don't know what the security status would be of a certain component because it might not yet have been decided, or it's coming from, let's say, a third-party vendor, and we might not have the full insight in their implementation. So then it means that we can put a probability between 0 and 1 to say that we don't know, or maybe we don't believe the input data, or maybe the input data, the security review is somewhat outdated. That means that we could set a probability to the presence of vulnerabilities in the model. And what the insights you would get from that is that you could see what is the expected impact or importance of this vulnerability as seen from the total impact on the architecture security. So 50% in this case, it means that we don't assume that this application is completely clean and completely safe. But on the other hand, we don't assume that it is a walk in the park to make use of this one either. And yes, so as you can see, there are no IT specific aspects in this to these modeling objects really. So for this, let's see. Yes, here we see that this object here is representing allowed communication between two endpoints. This one is about what you can do with a piece of communication is that you can do denial of service, you can transmit, and you can transmit a response. It doesn't say anything about ARP cache poisoning and things like that, because that's kind of IP specific. Likewise, if we look at this network object here, even though it has got a network icon to it, it is about access and access to network data, bypass access control if there is something like that, and eavesdrop and so on. And these are attack steps or operations that are applicable to any kind of communication slice, really. So if I think about the vehicle-oriented presentation that I'm going to do in an upcoming session, we have this CAN bus concept, and the CAN bus concept it inherits several of these attack steps and these possible operations. The difference is that if an attacker need to make use of or work its way through a different type of architecture or a different environment, It is more about that the attacker need to have the proper tooling and experience and so on. But the types of operations, they will be very similar. In the other end of this architecture, we have connected an attacker object, and this attacker object is defining the starting point of this attack scenario. And we have connected this one to the internet because that's that's the most obvious attack vector, of course. But other attack scenarios can be investigated as well. So this attacker can be connected to an internal system. It can also be connected to, let's say, it could be connected to an internal system which is connected to, let's say, service workshop. And if the service workshop is not expected to have an entirely uncompromised or clean IT environment, then there will be some allowed communication, of course, because service is supposed to be possible, allowed communication with the onboard systems. And that means that we could analyze how difficult would it be for an attacker to go from a workshop system into the onboard systems of a vehicle. And that will depend, like with the discussion so far, it will depend on two things essentially. What is the structure and reachability from the entry point into the vehicle, and what are the security measures or the the defensive obstacles that the attacker need to bypass in order to reach further into the vehicle or start getting a foothold and so on. So the methodology or the techniques that the attacker would use are quite different from attacking a web application, for instance, but the procedure that the attacker would follow would be quite similar. So the purpose of having an attacker in this model here, so far this is about threat modeling and setting up, let's say, this CAD version of the intended architecture. And if possible, it is possible to collect information or detailed information about the different parts of this architecture also, of course. So if you have this initial diagram and you have very detailed information because you have made a security review of a couple of these components, then you could make more detailed representations of certain subcomponents here. But the intention of having an attacker here is, of course, to run attack simulations. And attack simulations will behave like this is the starting point. So in this case, the attacker has got access to this network zone. And the mindset is like, okay, what is expected to happen next? Well, the intended use for a regular user is to be able to sort of visit this web server here. Or if this is the workshop, it is intended to be possible to connect to the correct entry point to the onboard system. Then, if you can do that, what is going to happen next and so on. So to answer what is expected to happen next, we skip out of this. We have attack simulations that we can run. And if I open an attack simulation of that example model, we can check out a report that we get, and here we see something called high value assets. And these high value assets, they are specific objects in the model that have been selected to be presented here because they are considered to be particularly important to the functionality of the architecture or the solution. In the case of this Singaporean example here, it was about a front-end web application. You had some application server in between and then a database server and so on. So in that case, in the classic traditional example, it is the customer data. So that's why the data is shown here. And if we check the critical path, we see the path of least resistance from the attacker's entry point and going over to the high value asset on the side. It's quite some bit away. There we go. Here we have the data right, which is the final goal of the attacker in this scenario. So we see that we have the entry point here, which is access to the first network zone, and then we have this front-end application which is part of this web server that we saw, and it says network connect. Well, this is not really an attack step from a security standpoint because, well, regular users are supposed to connect here. But attempt to use vulnerability, that's not really intended. And then we see the first phenomenon of this unknown server-side vulnerability, because in the high-level architecture diagram, we don't have information about the security status of this one. So here we have a representation of the case that there might or might not be some security issue here that the attacker might make use of. And if we continue, we see that if you manage to gain access to the first application, you will be able to make contact with other applications. In this case, of the web application being run by a web server, you will be able to contact the local web server. And you, if you, let's say, if you do who am I in this one, you will see that you are likely www data, and that means that you can authenticate to whatever the web application need to authenticate to. So that gives you a little bit of access, which means that you can use that access to proceed into other parts of the diagram. And if we look at, this is the path of least resistance. And then there are other less likely paths that are going to show up. In a simple diagram like this, we have only one simple here because the architecture is very limited when it comes to connectivity. We only have the possible communication between objects that are represented by the sort of black arrows in the architecture. And that means that other means of communication is not expected to be possible. This can be added by saying that, okay, we have a firewall between two network zones here. There might be additional connection rules or additional communication options between the network zones or between the communication buses. But the first option is, from an attacker's perspective, is always to try to make use of already allowed communication. So that's for the attack simulations. And if we, and these warning triangles here and so on, they of course indicate things that can be investigated further or improved. Yes. Then when defining these kind of modeling objects or applications and their corresponding vulnerabilities, and if there are user accounts in there, there might be default passwords, or for performance performance considerations, there might even be that there is nothing like an access control, because both two endpoints are maybe considered to be part of the same solution. So when looking at that, let's say I have an example of, this is from the power industry, of course, but it is still an industry-specific SCADA-related device. And this one doesn't really look like a computer, but it has got a network connector here. And if I look at the specification of this smart RTU here, I get to know a lot about electrical properties, and I get to see that there's a couple of communication protocols like Modbus and so on supported. But I don't see much about what an attacker is expected to see once it can reach and start talking to this device. So another way of looking at this is to look for, well, either do a white box review of what's in this one anyway, or you could take a look at ExploitDB, and here we find it. It says Mitsubishi Electric, but of course other vendors have their problems. But as we can see here, it is a PHP implementation, which you see that it's running on, it's accepting requests over HTTP, and what the payload here says, it says sudo, and it says netcat, and it says ping check. So this is actually a Linux machine. And suppose that that's also an interesting aspect of threat modeling. Suppose that you don't have this particular device with this particular vulnerability, but you might have a similar device, maybe just a different version, or you have in a broader perspective, you might have a device or an application for that matter, which is sort of performing the same kind of task. Then it might be the case that it has got the same properties and the same security issues or similar security issues. So in that case, what you can do with threat modeling is to put a probability to, well, what if I have a security issue in this component here? How is that expected to impact the general security of the solution? So that really concludes my little speech on the threat modeling and attack simulation view on different industry-specific devices, and how you would make use of threat modeling different architectures where you have kind of limited information, or when a lot of aspects might not yet have been decided. So then I hand over back to the moderator and check if we have any questions so far.
All right. Thank you, Joar. So a question is, you mentioned something about vehicle specific support using securiCAD. And you also showed some examples of different industries making use of this, let's say, methodology that you propose. About vehicle-specific support, can you give some more insight on what's going on there on that front?
Yes. If I skip back to showing the model here. Yes, this set of modeling objects here, and you see them in the main model as well. They are really the basic building blocks for this kind of model. And in the vehicle world, so to say, instead of network, you would have things like Canvas, and instead of application or a server and things like that, you would have an ECU running different pieces of functionality. And that is something that we have a different set of modeling objects for. So that's a different modeling language, as we call it. And that one is more or less based on this approach. So that's why I would like to, I wanted to present these basic building blocks first, and to set the concept, so to say. And then the next session, I would like to show what vehicle-specific modeling objects we have here and what their attack steps and defenses would be.
All right. And I guess when we talk about vehicles, well, the first thing that comes to mind is the car. But in the automotive industry, there's a lot going on also in the periphery of the car, like there's a cloud infrastructure,
Yes.
sensor networks in the roads, and all these things. So I guess there are also libraries. You mentioned something about libraries, right, of objects. So those, I guess, there will be libraries of objects from other fields also that could, integrate well in an automotive scenario.
Yes, I mean if we think about let's say that you have tunnels with sensors and so on, then those devices, they are more close to the industrial control systems world with the SCADA structure, like this IEC 62443 and things like that. And that means that they are more similar to traditional systems. But then they all, of course, have a lot of interaction with sort of onboard systems. So that and also the workshop is a good example of that, of course.
Right.
So that means that you could you don't have to limit this model to just the onboard system, but you could have it as a part of a larger system, maybe representing a workshop or a factory for that matter, where you would have well, there's a risk of a supply chain attack, really.
Yeah.
And so other parts or other industries can be integrated within the same model like this.
Yeah. All right. And would you say it would be possible to have vendor-specific libraries of such objects? So, for instance, if we could have a manufacturer, having their own library.
Yeah, absolutely. And that means that we don't really, from this threat modeling perspective and attack simulation perspective, really, the interesting thing is to see a certain solution from an attacker's point of view. So what is a certain solution expected to present to an attacker when the attacker reached there? So that means that the implementation is not all that interesting, but the potential vulnerabilities or the possibilities that an attacker will see, that's the interesting part. And that means that components can be created by manufacturers or people that are familiar with the technical solution and say that, okay, there is an external endpoint here that is intended to be used. There might also be a service entry point. There might, and once someone authenticate, they will see this kind of, let's call it operating system, which in turn might have other functionalities that can be useful to the attacker. That means that components can be created, and some of the customers of foreseeti, they are creating the such components themselves, but on the other hand, they don't want to share them with foreseeti even.
Yeah, that makes sense. Okay, and from what it looks like is that you have the object library and then you build a graphical model of the application that you have in mind or in production. Are there any other facilities in place to automate part of this process or to make it easier or to integrate with other tools?
Yeah, I mean, the main approach that several of the customers use is to use the data-driven approach. And the data-driven approach is, to begin with, you have to collect information from something. And that means that you need to have at least a lab environment running. And then we support collecting, or we support pre-collected information coming from, let's say, firewall data or other information that describe what is possible to access from one point to another or from one application to another system. Then we have support for, of course, vulnerability scanner data and things like that. But when it comes to the industry sector, vulnerability scanning is often out of the question, both because of stability, but then also the vulnerability scanners might not be all that efficient because they don't generally have that good modules for very industry-specific things to investigate. So they will find the basics, but they will not find the very specific security issues. And that means that even though a vulnerability scan, if you feed that data into the model, you will get a more detailed model because there will be confirmed vulnerabilities present. But you can also, and it's also recommended to still keep the unknown vulnerabilities with a certain percentage in the model. So that means that if you patch away the known or confirmed vulnerabilities, you still have a possibility that the attacker can discover something that the vulnerability scanner missed. Or, of course, vulnerability scans are snapshots in time. So that means that the attacker might discover something that wasn't there when the vulnerability scan was run. But yes, the data-driven approach is, of course, the recommended approach.
All right. So from what you describe, and correct me if I'm wrong, this the process described is mostly during, let's say, the production and post-production phase of a product, right? When there's something running already and you can collect some data.
Yes, the data-driven, yes.
Yes, and but from your experience, would you say that it would be also possible to use this methodology of threat modeling in other phases of the product, let's say life cycle, in the post, I mean, the design phase and the concept phase?
Yes, I mean, this architecture diagram that we started with here, it could very well represent a solution that is still on the drawing board, so to say. So it's not yet implemented, it's considered. And we have an example with one of our reference customers that I'm allowed to mention, that is Swedavia. They, of course, have a whole lot of systems, and then they were procuring another solution, an additional solution from a vendor. and then there were a threat model were made with the existing systems, and then we had an attack simulation on that to check out the security status. And then the not yet installed or implemented solution was added to that according to the architecture documentation. And then another or a new attack simulation would say if this security, if the addition would have an impact on the security status or not.
All right. And final question is has to do with the validation of the produced models and of, I guess, the library of objects. You mentioned, for instance, that there is a vehicle-specific library of objects. And
Yes.
has this been validated? I mean, how well they describe the different components and the coverage of the sector and all these things. Have those been validated in some way?
There is a project ongoing at the moment for validating the modeling approach, really, compared to traditional penetration testing. But I would say that the model is as good as the modeling objects are. So if you have a lot of, if your model is very close to the, let's say, the running system, that means that you have vulnerability scanner data available, you might have firewall policies available, and you might have the Active Directory structure available so that you can see which user is allowed to access which database. Then you will have a very close connection between the model and the reality. But on the other hand, if you have a conceptual, or not a conceptual, but if you have a planned architecture that is not yet implemented, then the model will, of course, only partly be a representation of the upcoming implementation. And also it means that it is from, if we think about the modeling mindset, a model that would perfectly fit the running or final implementation. That means that it would only find the same things as, say, a vulnerability scanner would find, or a penetration tester. But the difference between the model and the reality is what makes it possible to really find the real what-if scenarios that makes it a bit like a future safe. What if something is going to change in the future? And that change might not be expected or intended, then what would the impact be of that?
All right, I see. And from what you describe, what comes to mind, a comment I would like to make is that, in traditional threat modeling and risk analysis, you do a lot of, you construct a lot of the attack paths that are possible, you enumerate your assets and all these things. And then you do the analysis with your risk exposure, as you mentioned, and the impacts and everything. And from what you presented, it seems that, like, given a proper quality of your model and of your library of objects, maybe even threat modeling and the risk analysis could be made obsolete as a practice. I mean, you just go, you create your model, and then you run the simulation, so you have everything already.
Yes. If you think about threat modeling as a task of figuring out what is possible to do once you have succeeded with something else, and defining the different attack paths and so on, that's included in the logic of the modeling language, with all these different attack steps and defenses.
Yeah.
And then finding the way, if something is possible because you have achieved something earlier, well, the attacker, then that is sort of what is constituting the attack tree. And the attack tree is something that the user doesn't see, but it is built up based on the model before the simulations are being run. So the simulation engine will really take care of that task.
And of course, I mean, ideally that would be possible. What I said, make traditional threat modeling and risk analysis obsolete as a necessity. But I guess the burden then moves from all these activities, the traditional ones, to constructing a proper library of objects, and that is thorough with good coverage and good analysis and everything.
And I mean, there might be cases when you need to represent things that you don't have the possibility to collect information about. So, for instance, if you have an architecture that need to make communication or interact with some other area, it could be another company, it could be another authority, or a component that you don't know much about, then it will be very difficult to create a very, very accurate component out of that. But that's where the probabilistic approach comes in, because you know that you make contact or make communication with this, let's say, a remote system, but you don't know much about it, except that you make contact with it. And it might be the case that others make contact with that as well. And there it's probably having communication with other systems in turn. And that means that you would represent that with what you know, which is rather limited. And then you can say, okay, what if an attack would enter through here? What is my sort of inner resistance against that kind of attack vector?
All right. Okay, there are no more questions from what I can tell. And so this sums up today's webinar. Thanks a lot for presenting. It was quite interesting, at least for me. And I'm really looking forward to your presentation on the use case on a vehicle infrastructure.
Yes.
Yeah. All right. Great. Thanks a lot. Thanks everyone for watching. See you on the next webinar.